Let us compare different functions of different algorithms. We're going to determine which is the better function based on our analysis, comparison of the asymptotic notation. So let's have this example. One algorithm that has a growth rate of n squared and another algorithm that has a growth rate of n cubed. So which has a better growth rate? If I say better growth rate, it has less number of time in processing our algorithm. So let's have n is equal to 1. So the result between the two notation is the same, 1, 1. But when n is equal to 2, okay, the effect for n squared, it will become 4. But for n cubed, it will become 8. And n is equal to 3, 9 for n squared, n cubed, it will be 27. As you can see here, as n increases, the difference between n squared and n cubed increase exponentially. So therefore, n squared is less than n cubed. Therefore, n squared is better than n cubed. Okay? So the lesser the value, the better in a function if we're analyzing the algorithm. Okay? The growth rate of the algorithm. Another example. Log n squared versus log n cubed, which is better? So just a review about our math, we could rewrite this log n squared as n log m. So we're going to use this form to compare the two given notation. So let's rewrite. So the first will be rewritten as 2 log n, and the second rather, 3 log n. So log n is the same between the two, but if we're going to compare the multiplier, this is 2, this is 3. Therefore, 2 is smaller. Therefore, 2 log n is less than 3 log n. Okay? Another example. So n squared versus n log n, which is faster, which has a lesser growth rate. So let's what do you call this? Let's transform n squared as n times n. Okay, and the second is still n log n. So they have common term, which is n. So why not divide both by n? So the result in the first will just be n, and for the second is log n. And we all know that log n is smaller than n based on math concept. Therefore, n log n is better than n. N is greater than log n. Okay? Another example. N raised to log n versus n square root of n. Okay? So again, based on our math concept, rewrite it as log n times log n versus square root of n log n. So let's start with the 2 raised to 4. So what is the result on the first? It will be 4. For square root of 10, it's still 4. So the same. But how about if n is equals to 2 raised to 8? For log n, it's 8. But for square root of n, it's 16. While for 2 raised to 16, log n will give us 16. Square root of n, it will give us 64. Based on this, log n is smaller than square root of n. Therefore, n raised to log n is less than n square root of n. So this is a better growth rate compared with n square root of n. Another example, an algorithm that has a growth rate of n squared log n, and another algorithm that has a growth rate of n log n raised to 10. So which is better? So again, so rewrite both based on the mathematical concept about logarithmic. So this will be written as, the first will be written as n log n, while the second will be n log n raised to 9. Okay, so we just left 9 as an exponent of this. Okay, and then as you can see, we have a common term, n log n. So we could remove it, and the thing that will be left on the first equation will be n. Here it will be log n 9 squared. Log n raised to 9 rather. Okay, and then both, let's get the logarithmic of both equation. This will be log n and 9 log n. So we have a common term, log n and log n. So which is better? Definitely log n, because we have a multiplier of 9 log here. So this will be bigger compared with this value. So when we substitute values, you will see the difference. This second growth rate is bigger compared to the first growth rate. Okay. Another example. So we have algorithm, 5 algorithms that run, first algorithm that runs in 10, second that runs in square root of n, third that runs in n, fourth log n, and 100 divided by n. So we're going to determine which is the best, or the hierarchy or the ranking which has a less growth rate. Okay, so let's consider n is equal to 2. This is the result. So for the first value, so n square root of n and log n is small compared with the others. And how about n is equal to 4? 10 is still 10. It means constant regardless the number of inputs that we have. So it doesn't have an effect. That's constant. Okay. Then for square root of n, it will be 2. For n, is 4. Log n is 2. And for 100, it's 25. So in this algorithm, so as the number of n increases, the number of step decreases. Okay, how about n is equal to 64? Still, the constant is the same, square root of n, and n log 2n increases as n increases, but here it decreases. How about n, 256? Constant the same, 100 divided by n less than 1, and the highest is n compared with the other two algorithm. And in case it's n is 1024, n is bigger. Second, 32 square root of n log n, and then 10 is still 10, and 100 divided by n is still less than 1. So when you increase this, which is have a better result, 10 or log n? Definitely 10, because when we increase more the value of n, this will increase. It will become more than 10, but in 10, it's still 10. Okay, so therefore, when we rank it based on the growth rate, so n is greater than all algorithm, then followed by square root of n, followed by log n, then 10, and the smallest growth rate is 100 divided by n. Okay, so just a summary, constant is less than the growth rate with log function, and constant log function is less than polynomial, and the highest growth rate is the exponential. So for example, so we have constant 1 less than log n, and it's less than log n, and less than square root of n and n square n log n, but everything here is less than n squared, then the highest is n raised to n. So this is the order of our growth rate. Okay, constant, it has a least growth rate, exponential has the highest growth rate. So when we design our own algorithm, be sure we're going to minimize the growth rate. So if we could make it a constant, better. But if not, at least a logarithmic function. So it means at least it is minimized, not exponential. Okay, so that's it for this video lecture. On the next, we're going to discuss worst, average, and best case analysis of algorithm. So thank you for listening. See you.